This assignment begins with a really interesting application, which is that of a geosynchronous satellite. It turns out to be possible that you can launch a satellite into orbit around the Earth in such a way that its orbital period is the same as the rotational period for the Earth. What this means is that if you were to look up in the sky and search for where the telescope or where the satellite was, the satellite's position in the sky would rotate along with the rotation of the Earth, which means the satellite would be at the same location in the sky always. This is the reason why it's possible for us to, on the surface of the Earth, to point a satellite dish at a particular location in the sky and receive a signal from a satellite, also to transmit signals to that satellite. Otherwise, if you put a satellite in any other orbit, just like everything else in the sky, the satellite would rise and set as the Earth rotates and as the satellite orbits. And this is true for a lot of satellites that don't require being stationary in the sky. Well, for example, you want your spy satellites to travel all over the surface of the Earth. You don't want them just looking at one point, one side of the Earth all the time. So we want to be able to put a satellite into geosynchronous orbit. In order to do that, I'm going to use the Newton's universal gravitation form of Kepler's harmonic law. That is the time period of a planet's orbit squared, or in this case, a satellite. The time period of the satellite squared divided by the average radius of the orbit cubed is equal to 4 pi squared over g times the mass of the body that's being orbited. Now what we want to do is we want to figure out what is the radius of a geosynchronous satellite orbit. And so I need to do a little bit of algebra to solve this equation for r. And when I do that, just going through all the steps, you should come up with the radius of the satellite's orbit is equal to the cube root. That 3 is there to indicate a cube root, not a square root, of the universal gravitational constant m over 4 pi squared, the time period squared. Now, in order to plug things in and get the right answer on this one, you have to have the universal gravitational constant, 6.67 times 10 to the minus 11th. The mass of the Earth, the mass of the satellite doesn't matter. It's the mass of the Earth that matters. Mass of the Earth, you can use 6 times 10 to the 24th kilograms divided by 4 pi squared times the time period of the Earth squared. Now, because of the units of the universal gravitational constant in this, you're going to have to use the time period of the Earth's rotation in seconds, which means you're going to have to take 24 hours in a day, 3,600 seconds in 1 hour. Square that, calculate it, and you'll find the radius of that you would have to put a satellite. So it would orbit the Earth geosynchronously. It turns out that radius, when you find it, is many multiples of the radius of the Earth itself. This orbit is much larger than the radius of the orbit of, say, the International Space Station, which orbits the Earth about once every 93 minutes. This is a fun one. I think it's possible that many folks out there don't realize that astronomers, using our most modern, sophisticated techniques, have discovered planets in other solar systems. In fact, these planets, which are called exoplanets, because they're planets outside our own solar system, we've discovered hundreds of them. So commonplace is finding these planets that really the interesting focus right now is trying to find one of them that is Earth-like, a planet that we could, potentially travel to and arrive on the surface and find it to be very hospitable to Earth life. At any rate, one such exoplanet is WASP-32b. Lovely names for these planets. Anyway, what we want to do is we want to figure out what the radius of this planet's orbit is around its own sun, and compared to the orbit of the Earth's radius around our sun. You may have heard this thing about the habitable zone, that there is a region away from a star where we want to look for habitable planets, because if you get too close to a star, it's too hot. If you get too far from a star, it's too cold. You want to be right in the habitable zone, sometimes called the Goldilocks zone, because of the Goldilocks and the bears, and this chair is just right. So anyway, so once again, I'm going to use the harmonic law. T squared over the average radius cubed is equal to 4 pi squared over gm. And once again, I'm going to solve for the radius. Oops, look, another mistake. I left the cube root out. That root there needs a 3 on it. That's a mistake. Heads up, it's not the square root. It's the cube root. I would go back and change it, but it's just advice. My advice is that you do a cube root there, not a square root. Those who just look at it without listening to the words are probably going to have a hard time getting this right. Anyway, so now I just have to calculate. Well, there's a little bit of trick to calculating this one because we want to compare the radius of this planet's orbit to the radius of the Earth's orbit around our own sun. To do that, what we're going to do is for the mass of the object being orbited, we're going to use 1.1 times the mass of the sun. Mass of the sun's given in the statement of the problem. We're going to use 1.1 times that mass because this exoplanet orbits a different star. It's not our sun. It's very, very similar to our sun, but it's not our sun. 1.1 the mass of the sun. Now, when we put the time period in, we want to put that in Earth years. But the time period of the planet is given in days. In fact, it's a very short number of days. The way we put that into Earth years is to take that number of days that's given for the planet's orbital period and divide it by 365, because there are 365 days in an Earth year. That way you're putting the time period in Earth years. What that does for you is it's going to give you your answer for R in terms of Earth radii, that is the radius of the Earth's orbit around the sun, which is called an AU. So, if you use the mass as 1.1 times the mass of the sun, and you use the time period in this equation as the time period of the planet divided by 365, and you remember to cube root it instead of square rooting it, you'll get the radius of WASP 32b in astronomical units, otherwise known as AU. Next up is a tale of two satellites, satellites A and B. And at first blush, it seems like a complicated problem because satellite A is doing this and satellite B is doing this. And what are we going to do with that? Well, the question is all about the orbital speed of these two satellites, satellite A and B. And I have an equation for that. The orbital speed of a satellite is the square root of the universal gravitational constant, the mass of the body that is being orbited, divided by the radius of the orbit squared. But in order to answer this question, I don't need to do a lot of calculation. First of all, they want to compare the speeds. How do the speeds compare? Well, they tell me that one satellite has a different mass than the other. Well, I don't care that the masses are different. Notice in my equation for orbital speed, the mass of the object that is orbiting, it does not come into it. I need the mass of the object that is being orbited, in this case the mass of the Earth, but I don't care about the mass of the satellite, which is really nice if you're in the business of building satellites. You don't have to worry about how massive your satellite is. For example, we just did that geosynchronous orbit thing. Imagine if you wanted a geosynchronous orbit, but it had to be exactly a certain number of kilograms. That would be really tricky to technologically design a piece of equipment that would have exactly the right mass and end up in exactly the right place. It'd be tricky. So it's not mass dependent. Mass doesn't matter. But I can't even remember the question at this point, but I think it says that B orbits at a radius that's twice as far away. Well, if it's twice as far away, then I'm going to double the R in the denominator. And so I'm going to decrease, because a larger radius, obviously with the radius being in the denominator, results in a lower orbital speed. But the radius is inside a square root. So if I double the radius, I'm decreasing the orbital velocity by a factor of 1 over the square root of 2. So a little bit of reasoning of proportionality like that will get you through this problem, hopefully without any trouble. It's not surprising here that I have an ISS question, the International Space Station. It's the most well-known, recognizable satellite body that we currently have, and what we have some questions here about the orbital mechanics of the International Space Station. First of all, it tells us the altitude of the International Space Station above the surface of the Earth and asks us to calculate its orbital speed. Calculating the orbital speed is easily done. I've got an equation for that. The orbital speed is equal to the square root of the universal gravitational constant times the mass of the Earth, because the Earth is being orbited. It doesn't matter what the mass of the space station is. As a matter of fact, the mass of the space station changes as we add bits and pieces to it. Astronauts come and go, and so forth. Divided by the radius of the satellite's orbit. capital R. You have to be careful here because you're not given the radius of the orbit. You're given its altitude above the surface of the Earth. You have to take that altitude and add it to the radius of the Earth to get the full circular radius of the orbit of the International Space Station. The radius of the Earth, by the way, it's totally okay to use 6.4 times 10 to the 6th meters for that. Remember, everything in meters, kilograms, and seconds. You calculate the speed fairly easily. For the time period, I'm going to use the harmonic law again, but I'm going to do a little different algebra. T squared over r cubed is equal to 4 pi squared over gm. I'll solve for t. Go ahead and do that for yourself. But what you're going to get is that the time period is equal to the square root of, I haven't made a mistake, that's a square root, 4 pi squared over gm r cubed. So I'll just use 4 pi squared divided by g, 6.67 times 10 to the minus 11th. The mass of the Earth, 6 times 10 to the 24th kilograms, and the radius of the orbit cubed, which is once again the altitude plus the radius of the Earth. It occurred to me as soon as this question came up, and it was really surprising, that a thing that sometimes, well, perhaps people aren't aware of, is that you can see the International Space Station from the surface of the Earth because it's very large and it reflects quite a bit of sunlight. And so I'm going to post shortly to the Google Classroom instructions on how you can do that, because in these times of being cooped up inside, it'd be nice to have a little activity where you can go out and see something that's truly wonderful, like a man-made object orbiting the Earth. By the way, calculate this time period, it's quite short. I said 93 minutes or something like that between. But at any rate, keep an eye out on the Google Classroom for an opportunity to watch the International Space Station pass over.